Imagine you're building a machine learning system for a really high-stakes pathology lab. You get to work, you run your data, and you successfully build a pneumonia detection model. Great. It works perfectly.
Right, but then next month, the hospital's requirements change.
Exactly. They need a COVID model added to the pipeline. So, you dive back into your code, you add it in, done. But then 2 weeks later, they ask for anomaly detection for rare blood diseases.
And that's where the pain starts.
Yeah, you try to manage all of this with this massive script using basic Eiffel statements. You know the exact kind I'm talking about, like if model type equals pneumonia, run this pre-processing block.
Oh, yeah. If model type equals COVID, load these specific weights.
Right. And fast forward a few months, and 400 lines later, your script has entirely collapsed into this tangled mess of shared variables, hidden bugs, and config conflicts. The core insight here, scripts just do not scale. Real ML systems require modular components.
They absolutely do.
Welcome to the AI and ML YouTube channel by 60 Seconds Academy. Here we focus on practical and application-based understanding and concept clarification so that you can be industry-ready and apply your knowledge to real industry projects.
It's really fantastic to be here. I mean, that pathology lab scenario, it's almost a rite of passage for every ML engineer.
Oh, totally. We've all done it.
You start with a script because it's fast, it feels productive in that first hour, but then you quickly hit a wall where, adding just one new feature breaks 3 old ones.
And suddenly you're spending your entire weekend debugging an if statement. We've all been there, just staring at the screen at 2 a.m.
Yep.
Which is why today's deep dive is all about upgrading basic object-oriented programming, or OOP, into what we call ML-specific system design thinking. Looking at the notes we have today, the mission is incredibly clear.
Right, because this isn't just about, writing classes or memorizing Python syntax.
Exactly. We're getting into the ML object lifecycle, managing heavy state, mastering those mysterious Dunder methods, and ultimately building pluggable, scalable systems.
What really stands out to me in these sources is that a lot of developers, they come into machine learning from traditional software engineering, right? Like web development or mobile apps.
Sure.
And they try to bring those standard practices with them. But an ML system behaves fundamentally differently than a standard web app. If you treat a multi-gigabyte neural network the same way you treat like a user login object,
your servers are going to melt.
Literally melt. Yeah.
So let's unpack that right away. We're moving from why massive scripts fail to the core difference between normal software and ML engineering. And reading through our notes, it all comes down to this concept of state.
State is everything here.
Right. In normal software, an object's state, which is the data it actually holds onto in memory, is usually tiny. Talking about a few string variables, maybe some integer user IDs, a Boolean flag here or there.
Exactly right. A standard object might hold, a few kilobytes of data? It's incredibly lightweight.
Barely anything.
Yeah, as a developer, you can create and destroy tens of thousands of those objects in a fraction of a second, and your operating system's garbage collector cleans them up without breaking a sweat. You don't even have to think about it.
But in ML, the state isn't just a username. The state consists of learned weights. It is the mathematical representation of the entire data set you just trained on.
It's massive.
It is. So here's an analogy I love from the notes. If standard software objects are like moving boxes filled with feathers, ML objects are moving boxes filled with bowling balls.
That is the perfect way to visualize it. You don't just casually toss a box of bowling balls around your living room.
No. Even a tiny localized machine learning model might be 50 megabytes. But a large language model or a high-resolution vision model, that spans multiple gigabytes of memory.
And if we connect this back to the foundational knowledge we covered previously in APML 5 regarding memory constraints, you realize that bringing a multi-gigabyte object into existence, it requires a fundamentally different mental model.
Right.
Creating an ML object is absolutely not a cheap operation. It's a massive memory and lifecycle decision. When you type model neural net and hit enter, you are actively claiming a huge chunk of your server's RAM or GPU memory.
You're literally dropping a box of bowling balls into the middle of your server.
You are. And because these objects are so exceptionally heavy, we have to be incredibly strict about exactly when they are born, when they run, and when they die. We can't just leave them lying around.
So we have to master the ML version of the object lifecycle.
Exactly.
So, if packing these bowling balls into memory is this dangerous, how do we stop the system from dropping them? I want to walk through that life cycle.
Let's do it.
It starts with creation, moves to initialization, then execution, and finally destruction. But I want to know what that actually looks like under the hood in Python. Like, how does the system physically handle it?
Okay, so Python uses these special double underscore methods, often called Dunder methods, to manage this entire lifecycle. First, you have creation, which is handled by the new method.
Okay, new.
Yeah. In standard Python, you almost never touch this, but it's vital to understand what it's doing. New is the method that actually talks to the hardware or the underlying C-level memory allocator to carve out the physical RAM for your heavy object.
Wait, so new is literally carving out the real estate on the server, and then in it, the initialization step is just moving the furniture into the house.
That's a brilliant way to put it. New builds the house. Init furnishes it. Init is where the parameters, the tensors, and the weights are actually loaded into that allocated memory. You're setting the state.
Okay, so the house is built, the heavy furniture is inside. Now we need to actually use the model.
Right. Next is execution, handled by the call method. This is where the model runs its mathematical operations and processes your data.
Okay.
And finally, you have destruction, which is handled by delay. This is where the memory is explicitly released back to the operating system.
But looking at the source material, here is where it gets really dangerous. There's a massive ML-specific risk regarding that final step, destruction. Because most Python developers think, oh, I'll just let the garbage collector handle it.
And that assumption will crash your system in production.
Really? Just assuming the garbage collector does its job.
Yes. In standard Python, sure, the automatic garbage collector cleans up objects when there are no more references to them. But that collection isn't always immediate. It runs on its own schedule.
Ah, I see.
If your ML object holds massive tensors, high-resolution medical images from our pathology lab, or, massive numerical arrays, that memory can persist much longer than you expect.
So if I'm running a loop, say I'm instantiating multiple models to compare them, and I'm just waiting for the garbage collector to save me,
You'll hit an out-of-memory error, an OM error, and your entire application will panic and crash because the system is trying to hold on to 5 different boxes of bowling balls all at once, just waiting for the garbage truck that hasn't arrived yet.
wow, that paints a terrifying but very clear picture. Let's rewind a second to the init and call methods.
Okay.
Say we have a basic model class. We use init with self and wait to load the bowling balls, and then call with self and x to execute the math, maybe returning x times self.wait.
Right.
PyTorch relies heavily on this, right?
Yeah.
When you type model x in PyTorch, it's utilizing that call method under the hood, which internally triggers the forward pass.
It does. And beyond execution, you'll see other critical Dunder methods governing the dataset's lifecycle, like len to determine the total size of your training data, and get item, which the system uses to index into that dataset and grab specific batches during training.
Let me stop you there, though, because I'm looking at this separation between init and call, and I want to really deduce why it's built this way.
Sure.
If init builds the machine and call turns it on, why not just pass the data straight into init and do it all at once?
I love that you're questioning the architecture itself. Think about how a model is actually used in production. How many times do you need to load the multi-gigabyte weights into memory?
Just once, right, when the server starts up.
Exactly once. But how many times are you going to pass data through that model?
Thousands of times a minute.
Right. So call brilliantly separates the configuration of the model from its execution. This is the absolute bedrock of framework-level design thinking.
Oh, I get it now.
Yeah, if you combine them, you'd be forcing the system to reallocate memory, reinstantiate variables, and unpack those bowling balls every single time a new patient's X-ray came into the pathology lab.
Oh, wow. That would be insanely inefficient. You'd be bottlenecking your own server immediately, so you configure once within it, and you execute infinitely with call.
You've got it. And that brings up the next major hurdle. Once that object is set up and running infinitely, how does it process all that new data without causing errors, without drifting, and without breaking the whole system?
Right, which brings us to the critical rule from our sources. State versus transformation.
Yes.
If we want to prevent this heavy house from burning down, we have to understand what we can and cannot touch.
This is a rule that engineers often learn the hard way, usually after days of debugging silent errors. We've established that state equals our learned parameters, the heavyweights.
Right.
Transformations, on the other hand, must be completely stateless operations.
Let's ground this for the listener. What does a textbook bad design look like here? Let's say I'm writing a class to pre-process data for our pathology lab.
A terrible design is relying on state mutation. For example, writing a method inside your class that says self.data. Preprocess, self.data.
Oh man, I've totally done that in my early scripts.
Mhm.
You're actively overwriting the state hidden inside the object itself.
And it creates invisible side effects. The data is changing silently inside the object. Imagine you pass an image in, and the object secretly normalizes the pixels and saves it back to self.data.
Okay.
A millisecond later, another part of your pipeline, maybe an auditing tool, tries to access self.data expecting the raw image, but it gets the normalized version instead.
Oh, because you overwrote it.
Exactly. The system doesn't crash, it just gives you the wrong mathematical result down the line. It's an absolute debugging nightmare because there's no error code.
It's just silently wrong.
Yeah.
So the functional approach is the alternative. Instead of mutating internal state, we write a method like def transform self x.
Yes.
Return preprocess x.
Yes. You pass the data in as X, the method does its work on X, and it returns a brand new output. It never touches, alters, or even looks at self.data.
So the internal state of the object remains pristine and untouched.
Exactly.
You know, this immediately makes me think of scikit-learn. I feel like this is exactly why they designed their library the way they did. They deliberately separate the .fit method from the .transform method.
You're spotting the exact architectural pattern. Scikit-learn is the gold standard for this. When you call .fit, what are you telling the model to do?
You're explicitly telling it, okay, look at this training data, calculate the mean, calculate the standard deviation, and change your internal state to remember those numbers.
Yes, .fit is state mutating operation. It's allowed to change the state because that's the whole point of learning. But once training is done, you switch to .transform or .predict.
And predict merely uses that learned state safely. It applies the math, say, subtracting that learned mean from a new data point without ever changing the mean itself.
Right.
Because if predict changed the mean every time it saw a new patient's data, your model would drift into garbage within seconds.
I couldn't have said it better. The strict separation of state mutation from stateless transformation is what makes scikit-learn so incredibly stable in production environments.
Okay, so we now know how to build and safeguard a single model. We understand its heavy state, we respect its life cycle, and we know never to mutate its data silently.
We do.
But let's go back to our hook at the very beginning, the pathology lab. What happens when our lab needs many different models? The pneumonia model, the COVID model, the anomaly detector. How do we avoid that 400-line Eiffel spaghetti disaster?
This is where we introduce the factory pattern. It is the definitive solution to the pluggable system problem in software engineering.
Before we talk about the solution, let's really illustrate the pain of the problem. Why is that Eiffel chain so bad? Like, if model type equals XGBoost, instantiate this. If model type equals neural net, instantiate that. It seems straightforward at first.
It seems straightforward until you realize what's actually happening inside those if blocks. When you say if model equals pneumonia, you aren't just instantiating a model.
What else am I doing?
You're probably loading specific medical imaging libraries, unique custom data loaders, and specialized pre-processing logic. Then Aleph model equals anomaly might use tabular data, requiring pandas and completely different dependency trees.
Ah, I see. So your central execution script isn't just picking a model. It's importing a massive tangled web of different logic for every possible scenario.
Right. It creates extreme tight coupling. Every time the hospital asks for a new model, you have to open up the core execution script of your application, dig into that massive Eiffel's chain, splice in your new logic, and pray you didn't accidentally overwrite a variable that the COVID model relies on.
That sounds incredibly stressful.
As the system grows, that single script becomes brittle, fragile, and honestly terrifying to touch.
So to avoid this nightmare, you basically need a middleman, kind of like a restaurant menu.
Oh, I like that.
When I go to a restaurant, I don't go into the kitchen and tell the chef how to chop the onions for a burger versus a salad. I just hand my order, the string burger, to the waiter, and the kitchen handles the messy creation part behind closed doors. Is that what the factory pattern does?
That's a perfect analogy. Instead of putting all the kitchen logic in your main script, you create a dedicated model factory class. This class has one single job. It has a method called create, and you pass it model type. When your main application passes it a simple string, like XGBoost, the factory goes behind closed doors, handles all the complex dependency loading, and hands you back a fully instantiated XGBoost model, instance ready to use.
So my main application code never even sees the messy setup. It just says, hey, factory, give me an anomaly model, and the factory hands it over.
Precisely. It removes the if-else chains completely from your main logic. It makes the system wildly extensible. Next year, when the hospital wants a new predictive model, you just add it to the factory's menu.
You don't have to change a single line of your core application pipeline.
Exactly.
That is the ultimate plug-and-play architecture. If we map out how these objects interact in a complete, loosely coupled system pipeline, it looks something like this. You have a data loader object, which passes raw data to a transformer object, which feeds clean data into the model object, which finally outputs predictions to an evaluator object.
And because of this design thinking, each of those components is completely independent. The data loader doesn't need to know how the model works. It just needs to hand off the data. You can swap out a simple linear model for a massive deep learning model, and as long as they both have a call method, the rest of the pipeline doesn't even notice the difference. They are replaceable and independently testable.
All right, let's put this into perspective. I want to pressure test everything we've covered by looking at where engineers fail most often, especially when the heat is on in high-stakes FAing interviews.
Okay, let's do it.
Let's say I'm interviewing you for a senior ML engineer role at Google or Meta. I throw a classic system design problem at you. Where do most candidates completely bomb?
The first major red flag I see from candidates is what we call the God class. This is when a developer panics and crams the data loading, the pre-processing, the model architecture, and the evaluation metrics all into one single, massive, 1,000-line Python class.
It's the old 400-line script problem, just wearing an OOP trench coat.
Exactly. It shows a complete lack of modularity. The second red flag is tight coupling, which we just solved with the factory pattern. Candidates will write classes that heavily depend on the internal hidden variables of other classes. If you change the name of a variable in the data loader, the model class breaks.
And we also talked about hidden state mutation. Like, a candidate writes a pre-processing function that silently overwrites the input array.
Yep, that's a quick way to fail a system design round. But the most ML-specific failure is memory mismanagement.
Leaving large objects persisting in memory.
We see this all the time when a candidate accidentally writes self.data is huge enumky array inside a class that lives forever.
Right, they tie a multi-gigabyte array to the life cycle of an object that never gets destroyed. They basically cemented a box of bowling balls to the server floor. So what is the technical fix for that?
The fix is explicit lifecycle awareness. Using the command-del-self.data to explicitly tell the Python interpreter, I'm completely done with this specific chunk of memory, release it back to the OS immediately.
So you don't wait for the garbage collector to save you.
Don't wait. Prevent the memory leak before it happens.
I love this. So let's do some rapid fire. If I ask you the big conceptual question, why are you using OOP for this machine learning pipeline instead of just functional programming? What's the answer that gets you hired?
The answer that gets you hired is, I'm using OOP to encapsulate heavy state, those multi-gigabyte weights. I'm using it to ensure modular design with reusable components and, crucially, to exert strict, deliberate control over the object lifecycle so my system scales without crashing.
Perfect. And if I ask why PyTorch relies so heavily on the call Dunder method instead of just putting execution in it?
You explain that call enables that clean mathematical model X syntax. But more importantly, it absolutely separates the one-time configuration of the heavy model from its infinite continuous execution.
Okay, question 3. Why separate .fit and .predict?
Because fit changes the state it learns, while predict merely uses that state safely without mutating it.
Question 4. How do you avoid the ifelse model selection nightmare?
The factory pattern. You make it plug and play so your core logic stays clean.
And finally, what's the biggest OOP mistake in ML?
Oh, definitely hidden state mutation, tight coupling, and those dreaded God classes.
Brilliant. Interview passed. And now we want to challenge you, the listener, directly. We have a lock engineering checklist from the source material here.
This is crucial to actually applying this.
Ask yourself, is your state clearly defined? Are your transformations totally stateless? Are you using Dunder methods correctly? Do you understand the life cycle of your objects? Is your system actually modular, or is it a script in a trench coat?
To really internalize this, your micro exercise for today is to actually put this into practice. Open up your IDE, build a simple model class and a transformer class. Implement the call method for the model and a separate fit and transform method for the transformer.
And finally, build a model factory to serve them up based on a string input. Honestly, doing that exercise alone will completely change how you view your code.
It forces you to move from just writing functional scripts to actually architecting systems. It really elevates your mindset.
Which brings us to the ultimate equation of today's deep dive. ML system equals heavy state plus controlled behavior. Object-oriented programming and machine learning is absolutely not just about writing classes. It is entirely about controlling that heavy state and orchestrating system behavior.
I think that's the perfect summary. Engineers don't just write code. They design systems that manage memory, orchestrate behavior, and accommodate change. When the hospital's requirements shift, like in our pathology lab scenario, a well-designed system adapts effortlessly without a single rewrite.
So now that you've mastered building these independent modular components, what does this unlock next? In APML 08, we will tackle inheritance versus composition. You'll move from just building single, isolated components to designing highly flexible, large-scale architectures. It's going to be an incredible progression.
I'm looking forward to it. It really takes these building blocks we learned today and shows you how to construct the entire skyscraper.
Before we go, we want to leave you with one final, provocative puzzle to mull over on your own. It builds on exactly what we discussed today about heavy state and memory allocation.
Oh, this is a good one.
Imagine if Python's automatic garbage collector suddenly stopped existing tomorrow, just completely vanished. Based on what you just learned about the ML object lifecycle, new, ADEL, and heavy state, how would you manually architect the creation and destruction of a constantly updating real-time streaming model without melting your servers within the first 5 minutes? Good luck figuring that one out. Keep building, and we'll see you next time.